Interesting title. I love it. All right, good evening, Europe. Good morning, US. We have another wonderful lecture coming up. I'm very happy because it's from a friend and colleague from our Space Architecture Technical Committee. It's Christina Ciardullo. Okay. I just noticed that it's hard to spell the surname. Haven't heard it so often. She is an architect, co-founder of the award-winning space architecture firm Search, and PhD researcher at the Yale Center for Ecosystems and Architecture. She has degrees in astronomy and philosophy, and also a Master of Architecture from Columbia. With that, she bridges a career between practice and research at the intersection of the built environment and the natural sciences. Christina has worked in international offices in New York and Berlin. She has been leading design teams and won concepts with them, for example, for the world's largest astronomy museum, the German EXPO Sustainability Pavilion, and leading innovation for ecological coastline development. With the company Search, she has won 6 NASA Centennial Challenges, which have been exhibited widely. And one example, for example, is the collection that is exhibited in the Smithsonian National Air and Space Museum. In her work with Yale, Christina has also collaborated with the UN Environment Program. And here she has a thought leadership in the embodied carbon and urban agriculture. She was one of the lead authors of a recently published report, which is named Building Materials and the Climate. So I will put the link down later, and it's worth to have a look at it. And she has recently been awarded the 2023 American Institute of Architects Future Forward Grant in order to investigate science-based methods to evaluate the opportunities on one hand side and also the challenges of integration of vegetation in and on buildings. So Christina, thank you for coming. I'm very much looking forward to your talk and to your innovative thoughts of bridging buildings with natural sciences. Thank you very much. Welcome.
Thank you so much, Sandra, and guten Abend alle over there. Let me know if you can see my screen. Yeah. And just before, do you see it if I move? Did you see it move? Yeah? Okay. I also will stop sharing my video because sometimes that my bandwidth doesn't allow it, and there's some videos in this presentation. So thank you so much. How much does your building weigh? I started with this question from Buckminster Fuller. While it's a true and real logistical concern for the launching of a habitat and the weight of its payload for a spaceship, it's also a prompt for architects on Earth to question just how much material it has taken to construct our buildings. Have we been efficient with our materials? Have we tread on the Earth lightly? Did we leave a small footprint, whether that's a carbon footprint or water footprint or some other footprint? So you may have heard a great deal of discussion lately on carbon emissions and the need to reduce the carbon footprint of the built environment. So for the building industry, this means thinking more deeply about the relationship to the material cycles of our planet and the means and methods which have dominated the way we source and build buildings. From the work of the geobiosphere to make and produce raw materials, whether that be renewable materials such as timber, or non-renewable materials such as crude oil or irons and metals. And this is not from extraction through smelting furnaces or glue lamp factories, through transportation across material supply chains, supplied by faraway fossil fuels with air refreshed from distant forests, resources that include both material energy to construct as well as to operate and support human life, both the necessary inputs and waste energies. So it's almost strange that the building industry here on Earth has what seems like only recently come across this need to use quote unquote life cycle analysis, the accounting of all the impacts of our building material production, construction, operational, and disposal practices. We have, for what seems like quite a long time, been unconcerned with what is upstream of our design intent, taking for granted the standardization of materials and methods that make up current practice. Only recently have we begun accounting for all of these parts of our system. This type of exacting analysis, though, has been part of space architecture for decades. We couldn't intend to build a system for space habitation without accounting for all the inputs and outputs over time. How much material was required to produce and operate this building? How much energy do I need to run my operations? How much material do I need to extract in order to produce these parts? How can I reuse materials so I don't have to extract new ones? All of these questions of efficiency and circular economy are really fundamental questions for architects in space and Earth. And perhaps separated from the immediacy of connection to our resources, material, water, air, and biomass, we have forgotten our fundamental interdependency with the planet. And having forgotten it, we've continued to build as usual with extractive and energetically intense properties in a way that turns out is not sustainable. And as we move further and further from our planet without the possibility to continuously resupply, architecture building suits will need to be surrogates for all of the resources of an entire planet. So what we can say is that design for space is creating a human environment that operates within limited means and resources. And this design exercise will provide feedback for Earth buildings that must also act as though materials, energy, and resources were limited, which they are. In space, we come face to face with design requirements not unlike the sustainable drivers we're called on to respond to Earth today. Responsible consumption and production, clean water, sustainable cities, and smart communities. Our space habitat should be everything we hope to achieve in our terrestrial buildings, and it will be responsible for creating a circular economy in terms of clean air and water, food and waste recycling, creating healthy environments for humans. So what I want to do with you today is this is going to be kind of a two-part presentation. The first part is to walk you through some of the highlights of the report that Sandra mentioned, Building Materials in the Climate, Constructing a New Future. And then I'll just talk a little bit about why I think these same design principles are applicable to space applications and what terrestrial architecture seeking to reduce its carbon impact on this planet means for space architecture and what space architecture can teach us for Earth. So I'll start with the report and say that I'm one of many authors on this report. It was developed by the United Nations Environment Program, the Global ABC, the Alliance for Building and Construction, Yale Center for Ecosystems and Architecture, and other partners. So we have a large team of industry experts and academics and policymakers all responsible for this. I'm just one part of many, but I'm very thankful to be on that team. So carbon, why are we so interested in carbon? Carbon compounds regulate the Earth's temperature, make up the food that sustain us, and provide energy that fuels our global economy. And most of Earth's carbon is stored in rocks and sediments. The rest is located in the ocean, the atmosphere, and in living things like trees. These are the reservoirs through which carbon cycles. Through our industrial processes, we release increasing amounts of carbon into the atmosphere, and carbon is one of the most significant greenhouse gases, absorbing heat from the Earth's surface and radiating back, increasing global temperatures. So why increasing global temperatures and climate change is important varies for many, including issues of social justice, with rising temperatures having disproportionate impacts on emerging economies, which will contend with increased climate disasters, flooding, and changes in food production potentials. For others, this rapid change in the environment outpaces the pace of natural evolution for biology to adapt to new circumstances, thereby decreasing biodiversity. So it's important for us to identify not only why carbon is important, but why climate change itself is important. So increases in carbon in the atmosphere are largely consistent with increases in industrial production and the use of fossil fuels. In the building sector, we can see that since 1945, we have dramatically increased the use of fossil materials, minerals, and metals proportionally, as well as overwhelmingly increased the volume of materials we use in construction in general. So we're both increasing the quantity of construction as well as shifting away from bio-based renewable materials to non-renewables. And as the world economy expands and as living standards rise, the global use of raw materials is projected to nearly double by 2060. Under a business as usual scenario, floor space worldwide is set to double by 2060, and every 5 days, the world constructs enough new buildings to add another city the size of Paris. And given the increasingly furious pace and scale of global construction, the challenge of shifting away from carbon-intensive materials and methods often seems daunting and potentially impossible. But it's important to recall that even in the very recent past, building materials were not always carbon-intensive. Up until the mid-20th century, global material flows were extracted overwhelmingly from renewable biological sources such as forests and agricultural processes. And by the late 20th century, a preponderance of metals and minerals constituted the most used materials for the first time in human history. Just 3 materials, carbon, steel, and aluminum, are responsible for 23% of overall global emissions today. So the building sector in general is responsible for 30% of carbon emissions. But this is both embodied and operational. When we talk about embodied carbon, we're talking about the emissions and created from the production of materials, and operational carbon being the energy used to heat, cool, and ventilate our buildings and to run electricity in our buildings. So while overwhelmingly the focus has been on operational carbon and reducing the energy in our buildings and increasing energy performance in our buildings, because of that attention, we are reducing our operational carbon emissions, but as at the same time, the percentage of those emissions that have to do with embodied carbon is increasing. So if we look at this graph from the Carbon Leadership Forum, carbon, the embodied carbon comes largely at the beginning, at the build, but can also occur during maintenance phases and also at the end of life of a building. But the operational carbon we can continue to decrease over time as we both decarbonize our grid using cleaner fuels, using solar and renewable electricities, our operational emissions decrease, or as we improve our energy performance requirements. So that we're able to sort of take a grasp of, but at the moment the building is constructed, that's when we really use the most of our embodied carbon. It is really important to start thinking about the whole life cycle of the building. And I think if there's one sort of way of thinking that is the most sort of parallel with space architecture, it's really this idea of life cycle thinking about everything from the time we extract all the way to the end of use or reuse, and where things are going. And for Earth, this means that we have to change the way that we relate to others in the built environment. We have to come into radically new relationships with actors that are up and downstream in the building life cycle. So an architect may never really think about the waste recycling or the way that concrete is produced. But now we're at a moment in time where we have to be in dialogue with each other to understand sort of this whole system in order to create the true circular environment. So there are many material streams that are relevant for the built environment, and we analyzed a few of them. But as mentioned before, concrete, steel, and aluminum are really the largest contributors. And if we look at examples from a few different regions, we can see by both volume and mass that they are also the heaviest, and really they make up the superstructure of the building. And superstructure is really where most of our carbon cost is coming from. So in our report, we took an avoid, shift, improve approach. So we are avoiding by building with less and building less. We're shifting to bio-based building materials, which are lower carbon materials, renewable materials, and we are improving conventional materials and building processes. So we are trying to use the materials that we do use quite frequently, the non-renewables, in new and improved ways. And we call this the avoid, shift, improve approach. As you can see, we're projecting a scenario in which we use significantly less non-renewable materials, and when we do, we're using them in a circular way. Either you're using design for disassembly concrete, or recycled steel, recycled aluminum, or reusing masonry. And at the same time, we're projecting an increase in bio-based and renewable materials and different kinds of bio-based and renewable materials, but also in a circular way, not to repeat the problems of the past and sort of continue with a linear economy for biomaterials, but really also a circular economy for biomaterials. So a circular economy in buildings means transitioning away from the take, make, waste paradigm to reuse, repair, and recycle. In a circular economy, extending a building's life is the most valuable and least wasteful option. So first, reuse the buildings. The next best case scenario is to reuse components. This is substantially easier if design for disassembly has been incorporated into the early design stages of a building's construction. So this allows for the easy dismantling of building materials and components so that the value of these materials is retained. The next option is for material reuse and remanufacture if needed. This prevents the need for extraction of non-renewable minerals for new material manufacturing, hence reducing embodied carbon. In a circular economy paradigm of reuse, repair, and recycle, where waste is eliminated, the practice of recycling or downcycling becomes a last resort, as it is typically a product of lesser value. So there are opportunities to reduce carbon in each stage of building development. As with many things in sustainability, the potential to avoid is greatest during the planning and design phases. The first question is to ask whether anything new needs to be built at all. Alternatives to new construction could be explored for existing buildings, which is the case for most of the mature economies, where a majority of the building stock already exists. Increasing the use of existing assets and promoting renovation and adaptive reuse is key. In contrast, in emerging economies, much of the building stock is yet to be built. In this case, where new construction is a necessity, design should aim to maximize building lifespans through modular construction, incorporating design for disassembly, and promoting resource and material efficiency. At the end of life of buildings, the most common waste management strategy is demolition, followed by disposal of materials in a landfill. However, this results in a loss of invested carbon accumulated over the building's lifespan. Of the roughly 100 billion tons of construction, renovation, demolition waste generated annually, around 35% is sent to landfill on average. So diversion and innovation management can greatly reduce waste. Just to say that we can think about the idea of materials being, the buildings are future material banks. So when we think of the lifespan of a building, 100 years, 200 years, think about the potential to use those as material banks for the future. You improve conventional materials, and let me know if sometimes this doesn't play. So can you see this? Just give me a thumbs up or something if you can see it. Concrete is by far the most widely used construction material in the world, and it's responsible for the most embodied carbon in buildings. It's experienced tenfold growth over the past 65 years, compared with threefold increase in steel production. In many applications, concrete is used when lower carbon materials could suffice, largely because concrete has developed supply chain and infrastructure with ease of use and calculation. It's just the easiest thing for us to do. Many concrete buildings of less than 12 stories could shift to bio-based structural assemblies for everything but the foundation, and if sustainable materials were available. Cement is the binding material in concrete, typically comprising around 10 to 15% of the total. And cement is by far the most carbon intensive to produce within concrete. Cement production alone accounting for 7% of global CO2 emissions total. So not 7% of the building industry, but 7% of emissions total from the production of cement, the binder in concrete. It's also considered to be one of the most difficult processes to decarbonize. This is because the majority of carbon emissions are released in the chemical process of converting limestone to calcium oxide. And so there's an urgent need to substitute these conventional cements with low carbon alternatives, such as byproducts from industrial, agriculture, and forestry, and energy sources. Steel is the second most abundant material used in buildings. And steel production is responsible similarly for 7.2% of global greenhouse gas emissions. And most emissions are generated during three processes: when steel is produced from primary raw materials using a blast furnace, when carbon is needed as a reducing agent, and from the energy used to heat the melt. The most significant strides in decarbonizing decarbonizing steel are electrifying the primary production, so using using renewable electricity, ideally hydrogen, to produce the steel. The biggest challenge to using secondary steel production, to using recycled steel, is the limited amount of scrap. There's a large gap between the supply of recycled steel and the rising demand. And this is because steel is used in buildings for a long time, greater than 20 or more years, and there's a rapid growth. So we have less steel to be able to mine for recycled content. In aluminum, aluminum production contributed to over 3% of the world's direct emissions. Producing aluminum requires smelting, and that being by far the most energy intensive step. But this also means that producing aluminum from scrap can reduce the energy by 70 to 90%. So the most significant thing is to focus on the reuse of aluminum and the recycling of aluminum. Plastics are ubiquitous and popular due to their low cost and ease of manufacturing, typically used in buildings and pipings, windows, insulation. Recycling offers an opportunity to reduce the demand for new petroleum-based plastics, but the average rate of recycling is really only 9%. Plastics' low cost and ease of manufacturing have resulted in many different chemical compositions that pose technological challenges during recycling. So it's harder to recycle a wide range of non-standard chemical mixes. So low plastic recycling rates need to be addressed through both the standardization of chemical compositions and improved practices. To talk a little bit about masonry, at the end of the 20th century, structures made of earth-based materials housed around a third of the global population. And since then, it's fallen to only 8 to 10%. I believe a lot of the buildings that you may live in are and have stood the test of time are still made out of masonry. More recently, the use of Portland cement to stabilize masonry has really driven the carbon footprint up, as well as firing methods with high temperatures for clay sintering. But to improve the performance and durability of earth masonry, we have to, similarly to concrete, think about low carbon binders, renewable binders, and potentially alternative methods that are more akin to traditional methods instead of high fire furnaces. One of the most promising parts of this paper is really about the transition, the shift to bio-based materials. And this is both through their capacity to be processed at lower carbon footprints and as well as the possibility for them to sequester carbon as they're used. So timber is leading the way with advances in timber applications. Local and regional studies have found that mass timber could reduce global emissions by 14 to 31%. In the last 2 decades, cross-laminated timber has become an attractive alternative to concrete and steel because it is a comparatively high strength to mass ratio. It can be used for walls, floors, and ceilings. We should think about this as hybrid construction. And it's not necessarily that we need a building to be entirely wood, but we can use it in combination with reinforced steel, reinforced concrete or steel, in a very efficient way. The manufacturing of structural beams, however, does rely heavily on toxic chemical glues. So we have to focus on alternatives to these glues. At the same time, we need to be extremely careful about management of our forest systems. We don't want a situation where we're over harvesting. So we need to be incredibly diligent about afforestation practices and really relying on efforts to keep the pace of forests going at the same pace that we need those materials. Aside from timber, bamboo is a front runner for building materials due to its rapid growth and carbon cycle. Advances in bamboo building materials have paved the way for the use and integration of structural and engineered bamboos. And there's with a tensile strength that could be close to steel and a compressive strength twice that of concrete, can be used for columns and beams. But similarly to timber, much of those bamboo products are generated with toxic chemical treatments, which do drive up their CO2 emissions, making them, in this case, almost as carbon intensive as steel. So we need to really focus on alternative ways to really create those products without these glues. Biomass. So this is agricultural waste byproducts. So each year, an estimated 140 gigatons of biomass is generated worldwide. Relative to the current end-of-life pathways for biomass, landfills and incineration, we can really take advantage of the value in these systems. And we can talk about different opportunities that forest byproduct and agricultural byproduct really have in the market. We wanted to throw in the idea that materials could also be living. So we've seen an increase in the use of green walls and green roofs and vegetation integrated into buildings. We want to think about this as a material alternative. Of course, there's a balance between operational and embodied costs. Often the idea of adding weight and soil to the building, increasing the structure required for the building is sort of a negative, but the idea of potentials over time for either decreasing the energy needs for the building with vegetation acting as the insulation or as a thermal mass, as well as the potential for carbon sequestration over time if implemented at scale is something we really wanted to consider. So this is part of the discussion. So space. Now that we've looked at the issues of building materials and construction for Earth through the lens of carbon, it's kind of difficult to understand, well, what does this have to do with space construction? We're not interested in climate change on Mars. That's really, it's hard to make that leap. However, I think that, as we've said, that this idea of thinking about the whole life cycle of the building, thinking about where your materials are coming from, where your energy is coming from, well, what are you going to do when that material's life has ended? These are all questions that are really necessary for Earth and space. And I want to talk about a couple of different categories of that we might think about. The first is adaptable physical space. So living in smaller spaces, or in other words, at higher densities. In space, human beings will spend 100% of their time indoors. Our current space habitats are constrained by volume and weight. There's only so much area we can build. And so for now, we've lived in space, in small spaces. So physical space is also a resource which we have less of in space and on Earth. Coming to terms with how we view minimal habitable standards on Earth is a serious question for architects today. To what extent are we influenced by cultural norms of habitation sizes? Where do these cultural norms come from? Is it from the critical size of the human body? Is it more cultural? Meeting the demands of affordable housing for a rising population is predicted to double the amount of constructed floor space. That's why we're constructing, the city of Paris every 5 days. Uncomfortably, in the last decade, in the developed world, the standard of living has risen such that we have increased our desire for more build space per person, but more materials and more space per person has its cost on sustainable developed. In these more developed countries, the amount of living space per person has also doubled due to aging populations and more people living alone, as well as those increases in standard of living. So building more means using more land, more materials, more energy, more resources per person. So many in the building industry have advocated for a shift in consciousness in relation to the expectations of floor area. And this is a very difficult thing to start to talk about. Learning to thrive in smaller spaces might mean we need to become more creative. It's not about living ascetically, but about living well and fully within limited means. This transforming apartment in Hong Kong on the left pulls out all the functions of a home in the size of a small studio. And it's very similar to this building on the right. It's a multi-purpose space required for small deployable habitats. This is from Liquifer's She Habitat. The next thing we could talk about is deployable construction. The discussion around design for disassembly of components, prefabrication, waste reduction, and reduction in on-site construction emissions have many similarities with space construction. In the 90s, NASA developed this useful classification system describing Class 1 habitats as fully outfitted and flown and assembled. Class 2 habitats as habitats deployed and assembled on site, and a Class 3 habitat primarily based on in-situ resources. And I would say that most of the recent habitat concepts over the past few years have really been somewhere between a Class 2 and a Class 3 habitat. These classifications are useful when we think about Earth and space synergistic applications, not as not particularly like naming in a particular system like additive manufacturing, but as the performance of deployability and on-site precision. One of the most significant environmental impacts of the building industry is the production of a significant amount of construction waste. It's estimated that building waste, as we've said, occupies 30% of the world's landfills. So we're not maybe concerned with waste buildup on the moon or Mars yet. Maybe we should be, but we are interested in the use of less materials overall. And in some of the key requirements for pushing Earth towards a circular economy is reduction of building waste, both at the construction site as well as at the end of life. Using automating construction in space is necessary to be able to construct before humans arrive, and no humans on the job site means less accidents. Additive manufacturing is one means of building autonomously, but the kicker for Earth is the ability to reduce on-site waste both through precision modeling at the design stage, as well as precision construction on site. So we're using, if we're going to use concrete, we're going to use the most optimized, limited amount of it as possible, and we're not going to waste it we're in the design phase, we're going to be optimizing for it, and on site, we're not going to be wasting it. It is quite advantageous that Class 2 deployable habitats made of deployable parts assembled on site is more of a near-term reality, both, I think, in terms of for Earth and space. On Earth, we could very much benefit from prefabrication and assembly of systems that have been manufactured off-site. And this also will reduce material waste during both the production of materials and the construction waste at the site, as well as designing for disassembly, which means that at the end of the building's lifespan, we can potentially take and reuse components in a way that doesn't devalue those materials. Material intelligence. In space, we do not have the luxury of mining infrastructure, transporting, smelting furnaces. We only have the very precious equipment that can fit in a few transports. So it requires us to think differently about how we source and produce those materials, which is really interesting. So while we've discussed the benefits of additive manufacturing, we still can't escape that concrete is by far the leading contributor to carbon emissions. So we've discussed that what we need to do is think about finding alternative binders, including circular and bio-based products. On the right is a structure designed with a plant-based composite. So the hope that being within our spacefaring infrastructure, we might imagine growing plants that are not only for food, but for fiber as well. And similarly, on the left, we're talking about using cementitious materials from renewable alternatives for concrete on Earth. So sourcing one's own renewable materials offers us a great glimpse into what it might mean to work without extractive processes. Would it be more effective to grow our own materials in space? We do rely on fibers for so many of the products of life, clothing, fabrics. For long-term habitation, we might find that renewable and grown sources of material aren't necessary. On the left is an image of CLT construction. And on the right is an idea of a bamboo environment for Mars, where I'm not quite sure about whether we can use it to enclose our structures. Potentially, if it has some tensile strength similar to steel, why not investigate some fibrous materials? Perhaps in the more immediate future on the Moon or Mars, we would not be concerned with metals and minerals, but with the energy and machinery required for processing those materials, so we can create synthetic fibers. We can talk about creating synthetic fibers as well. Energy and passive strategies. So what does energy and operational energy have to do with embodied energy of materials? It's really deeply embedded. I'll stay on this slide. It's deeply embedded within the use of materials, the impact that those materials and formal choices have on the operational energy of the building. In millennia past, we had vernacular architectures which showed us passive means adapting to our harsh climates. The use of masonry structures was not only to hold up a building, but really to regulate temperatures inside the building, especially in particular climates. So here in the Mars X house on the right, we looked at these deep overhangs and horizontal lighting and horizontal letting light in from the side to shield us from solar radiation, which was very much inspired by ancient Native American cultures, which used the natural overhangs of cliffs to protect their buildings from the sun, using the adobe materials that would absorb the heat of the day and release it over the cold desert night. So the relationship between materials and building energy use is critical. What would it mean for us to return, instead of relying on machines, HVAC, mechanical equipment to heat and cool our buildings, really returning to passive strategies, using the intelligence of form and materials to respond to our environment? Can we return to concepts like trom walls and materials that absorb and release heat over time, learn from ancient material wisdom to talk about how we might rethink the materials we use for space? So, in the Mars Ice House on the right, we looked at the fundamental physics of water as a radiation shield, as an example, but we used the potential for atmospheric carbon dioxide to act as insulation. So what I'm asking is to not only take the material solutions that we're used to on Earth at sort of face value, but to recall all of the properties of materials, structural, thermal, the properties that we are using to make a building stand up and condition it. And finally, I just want to touch on, we spoke about a shift to bio-based solutions, and this also applies to a shift to include circular and renewable resource management. So water, air, and the like. In space, we don't have the luxury to turn on the tap, plug in the computer, or breathe the fresh air. This reminds us that at home, as far as we can, we should contribute to the sustainable use and reuse of air, water, and materials within our built environment, and integrate the biological processes on which we depend into our urban futures. So the way we regenerate air, water, and nutrients is through our interactions with plants and microbes. And so similar to the idea of thinking about living biomass, vegetation as materials in our buildings, how can we, the future of our both our urban futures on Earth and in space will really have a necessity to look at that interaction between human and plant and microbial ecologies together. So that's where I'm going to leave you, as sort of all of these thoughts, food for thought, as you go out and design the future on any planet.
Thank you, Christina. How wonderful. What a great input. It fits perfectly well to our module. Okay. Daniel, thank you for clapping the hands. Maria has a question. Please ask your question. And
Yes.
the others, please put your question in the chat or just open your mic. Thank you, Maria.
Okay, first of all, thank you for your input. I saw that you had a depiction that described that recycling should only be used as a last resort. And I wanted to ask you why. There was also a picture that we should first of all reuse it, but by reusing it, you are more like restricted in the shape and the material. And is it the topic about recycling because it's too complex or too expensive, or why is it like that?
That's a great question. As an architect, I also want to be able to have the freedom to use materials in the way that I want to be able to use them. And so the idea of having to use something that was already in a particular shape or form is kind of off-putting. But the reason we talk about this is because there's a increasingly over the life of the building, we're putting more and more embodied energy into that building. And the more that we can use those materials in the form that we've put in so much energy to use them, the more that we're saving. So we can think about it as, obviously we can't have, not every building can be made of modular components. There is an amount of freedom, but can we think about how we could standardize some components and parts so that we can reuse them? So in this picture, the idea is that the highest use is to reuse the building. Obviously, you don't want to, like, it's more difficult, it's more energy intensive to take that building down and to put up a new one, even if your new one is more energy efficient and it's, it's obviously more beautiful, and it's just a lot of energy to take that building down and all the energy that went into producing new materials to make something new. So the first thing we want to be able to do is reuse the building itself, to adaptively reuse it, to change the way that it functions inside. And the next highest use being, okay, if there's modular components, are there modular panels? Are there, wall sections that have been designed for disassembly that we can reuse in a different way in a new building? And how do we change the way that we design to be able to work with standardized components, and still be able to be as innovative as we want to be with our buildings? And then potentially the step after that is, okay, so if it's not the whole panel, if we can't, reuse this whole insulated glass unit anymore, are there parts of it that are the components? Are there bolts? Are there struts? Are there things that we can still reuse in their material form? And I say that recycling is the last resort, because really you're reducing the value of that material. Once you've sent it to scrap, you're not, okay, for metals, for steel and aluminum, scrap is really great, and we have processes for renewing it, and low carbon processes for reusing recycled metals. But for example, if you wanted to reuse recycled glass or recycle masonry, there's a point at which there's a question as to the structure, as to the integrity of those materials over time. So really, we call recycling downcycling or degrading, and I think it's just this, like a thought that yes, recycling is wonderful, and we don't want to say we don't want to recycle, but the higher uses, the higher opportunities to reduce carbon come really from not totally reconstructing and rematerializing those materials, but to use them as they are. And how do we, as architects, work with those components is going to be interesting. It's going to be a challenge.
Thank you.
Yeah.
Christina, do you have examples from the US? Because in Europe we have a law coming up actually that the trend should be to plan already for these potential different uses, meaning that the components of a building have to be separable. And certain materials that are now in use, especially for insulation and, are not, or are with when you tear down a building. Do you have examples from the US where you have already integrated such an architectural approach?
Europe is far ahead of the US, and there's also there's much more legislation potentials in Europe also for, I think maybe this is what you're referring to, that like there's already laws against demolition of buildings as well. And I could say that the US is behind, as we are with many things. But yes, there's a desire to do that, but Europe is far ahead.
And how is it in the university? Because I also think this idea of planning a building already for its potential after use is new.
Yeah.
And students obviously should already, have this thought in mind in order to propose a design. How is it going at universities?
Well, I would say different at different universities, but I think I want to say first that in industry, there's still this idea of a building lasting for 50 years or materials being under warranty for 25, 30 years. This is really short. Our buildings, many of our buildings, especially the buildings that you live in, are much longer, have been around much longer than that. So I think that there's still a kind of mentality in many university settings that I've been in recently that we're still every time creating something new and creating something that is unique and innovative. And I think that we don't do as well of a job as we could of trying to imagine what does a century mean? What does 200 years? What does 500 years look like? And how different has it been between what we do now and what we did 100 years ago? And what can we project into the future? I think it's not as we don't do a well enough job of that, of thinking about this is not only now about representing the creativity of a particular style right now, but about projecting a timeline for your building that happens not only now into the future, but that happened when your building was extracted, from the ground. And I think it's an amazing way of thinking that we need to be doing more of. Yeah.
You're doing a great work.
Well, this is it definitely has been a major topic for the world recently, and that's why the UN Environment Program commissioned Yale to do this report. There's been a really wonderful increase in the amount of attention being put on embodied carbon, and sort of this life cycle thinking in general. And hopefully it becomes more standardized in the way that we design and build buildings.
I think maybe what Maria was referring to, because she is part of a design studio where we repurpose or recycle or upcycle even build materials that were trashed. So we use sun pine to build a structure. And this needs some creativity because, of course, you cannot use the material as it is.
Yeah.
You have to put them together and you have different requirements.
Yeah, absolutely.
It's a challenge.
No, that's right. It does take a lot of creativity to start to how you build new with these either components or panel systems or whatnot, whether it's a system as a whole or parts of systems. Yeah, it absolutely takes a lot of ingenuity to understand how to work with those and then to use them in as much as you can the form from which they have been disassembled. Like before you get to smelting down the bolts, can you reuse them in some other way?
That's why your Ice Hub project is super interesting, because that was also, I think this architect in an interdisciplinary team probably can do when they know, the environment. They come up with new ideas to use materials different. I think this Ice Hub concept was very an innovative approach of tackling an issue, because right before we had a talk by Peter White, and we know the radiation problem is not solved.
Yeah.
So you showed a wonderful way how architects can use creative ideas to find new solutions.
Absolutely. And I think, what was really interesting about this is also that we took water in a very first principles way. So we were collecting water in the Martian atmosphere. It would sublimate if it was exposed. So the idea of collecting it as a gas as it sublimates, storing it in its gaseous state. There was even an idea of just releasing the gas into a pressurized dome where it would accumulate on the surface of the dome and turn hard into ice. In this case, we also applied it as a liquid and then it froze on contact. Or that was the test that we did. And this material is very easily reused. You can simply, there's energy that it would take to melt that back down. But the idea of what are the basic fundamental properties of materials that you can manipulate and play with is it was very freeing to be able to, when you're in the space context, you're in what can we do? What can we think of? What can we do? There isn't this sort of immediate reaction to it's concrete. Oh, it's steel, or it's clad steel, or whatever it is. There's sort of that there is on Earth. Well, there's this whole new sort of blank slate that you have to be able to imagine what materials are from this moment that you take them out of the ground. How little energy can you put into them in order to position them in the way that you need them to do what you need to do.
It is a lovely example for a new creative way of how to deal with the environment, right? When you do your homework, of course, as an
Yeah.
architect.
Absolutely.
Are there any other questions from the students? Related to your work?
It's a lot. It's a lot. I encourage you all to read the building, go to the building materials and the climate.org, building materials and climate.org, and take a deep dive into that report. And I'm wondering for all of you, like what, how it changes, if it changes your perspective. Is this something that you've been thinking about all along? I'm sure Sandra has been directing you quite well. And I'm interested to know, your reactions on how it might change or not, or how it's been prevalent in your designs already.
All right, who can answer this question, please? One answer. How does the thinking about sustainability and the challenges have on Earth challenge your design work? I know you're all working on that, so please give me one answer. Maria, I ask you then, please.
I'm thinking, and I remembered what you told me, Christina, that it takes also a lot of creativity to recycle something. So I think it's really when we plan something or design something, it takes a lot of creativity, and with all the other input, it gets more, like you think out of the box. You're not inside it, then something like that. I don't know.
Yeah, absolutely. I think, that there's certain ideas that we take for granted. Like I just keep coming back to this. We draw things that we could have sort of assume are made of a particular material without even knowing that we're doing it. There's certain ways that we imagine buildings to be and look because that's the way that we are used to seeing them. And I also think it's really interesting, this idea that we didn't used to build with concrete and steel so much until very recently. Like that, the global cities were constructed out of earth masonry up until very recently, and timber, and it makes you think like we sometimes are so focused on the one moment in time that we live that and we take so many of these things for granted, and that's again why I love working in space. It's a moment for you to just remember, like reflect that that there are chemicals and physics, there's chemistry and physics in the world. It almost reduces everything to chemistry and physics and biology, and we sort of shed all of the means and methods and sort of norms that we are used to, and sort of get back to fundamentals.
Still, I think it's challenging or interesting that this, we have had another talk today from architectural philosophy that was interesting on space as a field, as a thought field, creative field. But in reality, it looks very different. So working in space as an experimental field is interesting and enriching, But it is still surprising that, for example, this resource question and this long-term sustainability aspect is not yet implemented as leading thought.
In space or here on Earth, or both?
Both probably, but especially in space, and there it is necessary.
I mean, it's sort of interesting that on the one hand, once we're spending billions of dollars to go to space and construct these habitats, and sort of like you can use as much energy as you need and use, we're already creating all of this infrastructure to be there. So, it's almost, in some people, I can see why some people sort of use materials and energy with abandon in space, because it's an amazing feat to do that already. But I just think that when we think about, like I mentioned before, like when we think that resources are limited, when we think that air and water and materials and energy is limited, space is limited, we get more creative, we get more, and ultimately that is more sustainable for us here on Earth. Again, we're not concerned at the moment with climate change on Mars, or maybe it's beneficial if there's climate change on Mars for human beings anyway. And we might not be concerned with how much construction waste we're dumping on the moon, although we're starting to get more and more worried about these orbital waste of all of our defunct satellites and whatnot. But so I can see why, there might be this tendency like, well, we'll just, build with abandon in space. But I think if we did take this idea of life cycle thinking and like the efficient, creative and efficient use of what we have, that would serve us in both space and Earth construction.
Wonderful. I would say that is a wonderful concluding thought, Christina. And I thank you very much for your talk, your input, and explanation of your own work, as well as the work that you contributed for the UN. And yes, let's work on a sustainable future here on Earth in space, right?
Absolutely. Thank you so much for having me.
Have a good day.
You too. Enjoy. Have a good evening, everyone.
Thank you.
Bye-bye.